Every tutorial tells you the same thing. If you are predicting a continuous number like a house price, use mean squared error. But if you are classifying an image like cats versus dogs, you must use cross-entropy loss. Why is that? What actually happens if you use squared error to classify a cat? Your neural network just gives up. It doesn't get trained properly. Why? Regression is about how far off you are. Squaring the error is great for punishing a $50,000 mistake on a house price. But classification is just true or false. The absolute biggest mistake a model can make is 1. If the truth is 1 and your model predicts 0, the maximum squared error is just 1. An error of 1 is a tiny slap on the wrist. It isn't significant enough for the network to drastically update its weights. To fix this, we need a loss function that violently punishes a model for being confidently wrong. To build it, we have to borrow a concept from physics. We need the mathematics of surprise. Think about how your brain processes information. If someone tells you the sun will rise tomorrow, you don't care. The probability is 99.99%. Zero surprise. That message contains basically zero information. But what if someone tells you you just won the lottery? Your brain lights up. The probability was microscopic, so the surprise is massive. So, how do we teach a neural network to light up when it's surprised? We use a math trick, the negative logarithm. If you plug a high probability like 0.99 into a negative log, you almost get 0. The outcome is as expected, no surprises. But if you plug a tiny probability like 0.01, the number explodes. It's a massive surprise. Let's bring this to machine learning. The simplest classification problem in the world is a coin flip, heads or tails. But a coin has two sides. To get the overall entropy, we just calculate surprise of heads and multiply it by how likely it is to happen. Then we do the same for tails and add them together. It's literally just the weighted average of chaos. If we just code this out, you can see exactly what this chaos looks like. Look at this curve. If the coin is rigged to be 100% heads, the entropy is 0. You know exactly what's going to happen. But right in the middle, at 50-50, the math peaks. You have absolutely no idea what the next flip will be. Entropy is just a mathematical ruler for measuring uncertainty. So, how does flipping coins actually help us train a neural network? In machine learning, we compare two things, the truth and the model's guess. We use binary cross-entropy. The math looks scary at first, but watch what happens when we actually use it. Consider the case of classifying if an image is cat or not. If the image is definitely a cat, our truth is 1. That means the entire second half of this equation gets multiplied by 0 and disappears. We are left with just our surprise formula, negative logarithm. Now, let's plot this cross-entropy loss and plot mean squared error right next to it. Look at the difference. This answers the question we asked at the start of the video. If the model is confidently wrong and predicts 1% cat, squared error barely reaches 1. It's a tiny pathetic hill. But with cross-entropy, it skyrockets towards infinity. This incredibly steep slope creates a massive gradient. It forces the neural network to wake up and fix its weights immediately. The math is beautiful. But if you deploy this exact formula to your production server today, it will eventually crash your entire training pipeline. Why is that? What happens if your model is 100% confidently wrong and outputs exactly 0? The computer tries to calculate the log of 0. In math, that's a negative infinity. In Python, that returns nan, not a number. Once a nan gets into your network, it infects everything, destroys your weights, and the training loop is dead. How should we deal with it? We build a safety buffer using e power -10, which is just a scientific notation for a microscopic decimal. We use the np.clip method to force any absolute zero to become a microscopic decimal. The math stays highly accurate. The loss still explodes to punish the model, but your server survives. Before we go, there's one final magic trick to consider. In our last video, we used statistics to find the best model using maximum likelihood estimation. Today, we used information theory to find the best model using cross-entropy. If you look at them closely, they are the exact same equation. Minimizing cross-entropy is maximizing likelihood. It is just two different fields of science discovering the exact same truth about how we learn from data. And with that, we have come to an end of the probability and statistics series. We know the geometry, we know how to measure error. We know what the bottom of the hill looks like. But how does a network with a billion parameters actually walk down that hill blindfolded? To do that, we need a compass. We need calculus. And this is what we are going to decode in the next series. If you prefer reading, a link for the detailed companion blog post and Python notebook used is in the description. If this video helped you understand cross-entropy and its importance in classification, hit that like button and consider subscribing to decode the complexities of machine learning. I will see you in the next one.